Going underground and underwater in war. Gem Gürdeniz. Turkey should use underground and underwater domains as force multipliers in the great power struggles of the 21st century. The 2026 Iran-US-Israel war will be studied for a long time in terms of many aspects of cyber, air, and naval warfare, as well as capabilities in areas such as air power, air defense missiles, ISR, intelligence, surveillance, reconnaissance, electronic warfare, ballistic, hypersonic, and cruise missiles, armed unmanned aerial and naval vehicles, UAVs, USVs, mines, and precision munitions. Yet perhaps one of the most important lessons of the war emerged not in the sky or on the surface, but hundreds of meters below ground. The underground missile facilities, command and control centers, storage sites, and production capabilities that Iran had spent years building inside mountains managed to survive despite weeks of intensive attacks by American and Israeli air power. These sites suffered serious damage under intense air attacks. Missile bases, production facilities, tunnel entrances, boat storage areas, and launcher infrastructure were significantly damaged. However, it was not possible to destroy the entirety of Iran's missile and armed unmanned system capabilities that had been moved underground. Some tunnel entrances were reopened, some facilities were returned to operation, and despite the heavy bombardment, Iran was able to continue missile launches, fast boat attacks, and UAV operations in later stages of the war. Assessments published after the war indicate that Iran managed to preserve a substantial portion of its missile stockpile and mobile launchers. Iran's major underground investment, built over the past 45 years since the 1980s, was tested for the first time in a real war on this scale. Iran's success here should not be measured only by the number of targets it struck. What matters is that it was able to survive against the world's two most powerful air forces.
In other words, Iran demonstrated an ability to preserve its capacity to resist even after the enemy's first and potentially lethal blows. It achieved this largely by going underground. This success in resilience will likely serve as an example for many states in the global south that may in the future be threatened, pressured, or attacked by hegemonic powers. The Earth's surface and airspace are becoming increasingly transparent. A very important transformation is taking place on the battlefield in the 21st century. Lessons drawn especially from the Russia-Ukraine war have shown that, thanks to satellite systems, cyber capabilities, synthetic aperture radar, SAR, electro-optical sensors, signals intelligence, unmanned aerial and naval systems, electronic intelligence, AI-assisted image analysis, and long-range precision-guided weapons, it has become extremely difficult to conceal large military forces on the surface and in the air. Detecting a tank battalion, an air defense battery, a missile launcher, a command center, a logistics concentration, or any object approaching through the air is now far easier than it was in the past. Moreover, the problem is not merely seeing the target. In modern warfare, the time between detection and engagement has also become extremely short. A satellite, radar, or unmanned aerial or naval vehicle detects the target, its coordinates are transmitted into the command network, and shortly afterward precision-guided munitions or an armed UAV are directed toward it. When artificial intelligence is added to this process, the decision cycle from detection to attack becomes almost automated. The fact that even vehicles located dozens of kilometers behind the front line can be detected and struck by UAVs has greatly increased the risk and cost of moving on the surface. In short, as technology makes the surface more visible, warfare is shifting toward invisible domains. One of these is underground, the other is underwater.
Underground warfare is not new. Humanity has used underground spaces, especially tunnels, for thousands of years. Since antiquity, tunnels have been dug beneath fortifications during siege warfare. One of the oldest and most institutionalized examples of underground warfare in Ottoman military history is found in the Lağımcı, or military miner, corps. Their task during sieges was to dig galleries beneath enemy walls, weaken foundations, and use gunpowder to breach fortifications. During the 1453 siege of Constantinople, Ottoman miners dug tunnels to reach beneath the city walls. During the conquest of Crete in the 1648-1669 siege of Candia, the Ottomans and Venetians effectively opened a second front beneath the walls through mines and countermines. During the First World War, kilometers of galleries were constructed to place explosives beneath enemy trenches. In the Second World War, Japan used caves and tunnels on Pacific Islands to withstand American air and naval firepower. In Vietnam, underground warfare reached another level. The Cu Chi tunnels were not merely passages in which soldiers hid. Command centers, hospitals, ammunition depots, kitchens, living spaces, and logistical connections were moved underground. The U.S. military largely controlled the skies and possessed a degree of firepower superiority over the Viet Cong that was not remotely comparable. Yet that superiority diminished only a few meters below the surface. Underground space acted almost as a force multiplier that reduced the enemy's technological advantage. One of the countries that took this approach from the tactical to the strategic level was North Korea. The destruction caused by American air superiority during the Korean War left a deep impression on Pyongyang. As a result, North Korea began moving not only its soldiers, but also a significant portion of the state's military infrastructure underground.
Command centers, artillery positions, ammunition depots, air bases, and later missile facilities were placed inside mountains. At this point, we are no longer talking about a few kilometers of tunnels, but about an entire military ecosystem moved underground. This approach is important for Iran as well. There are significant assessments suggesting that North Korean experience influenced the development of Iran's missile forces. Analyses published after the 2026 war also drew attention to lessons that former Iranian Missile Force commander Amir Ali Hajizadeh had learned from North Korea's underground systems. One of the most striking modern examples of underground warfare has also been Gaza. While Gaza's tunnels initially consisted of relatively simple structures used for smuggling, infiltration, and concealment, over time they evolved into a far more complex military infrastructure. Command centers, weapons depots, communications lines, personnel movement corridors, and long-term living spaces were moved underground. The strategic consequence was significant. Although Israel completely dominated the airspace above Gaza, it could not dominate the underground environment to the same extent. Iran and Gaza are very different cases, but they share one common feature: the use of underground space on a strategic scale to protect military capabilities from increasingly sophisticated sensor and intelligence systems. Iran, from tunnels to missile cities. Iran applied the underground logic seen in Gaza across a much larger geography and at the scale of a state. Behind this lay Iran's fundamental military weakness. Iran could not compete symmetrically with the United States or Israel in terms of modern air forces. It therefore built an important part of its deterrence and war doctrine around ballistic and cruise missiles, as well as armed unmanned aerial and naval systems designed to create asymmetric effects. Yet possessing these capabilities was not enough. They had to survive the enemy's first attack and be capable of being regenerated. Iran's solution was to move a significant portion of its missiles, armed unmanned systems, and similar capabilities into the mountains. This gave rise to the extensive underground complexes known as missile cities. These became large military facilities in which missiles could be stored, prepared for launch, mobile launchers could maneuver, and command and control activities could be carried out. The 2026 war became a real test of this doctrine. For weeks, American and Israeli air forces systematically struck Iran's missile infrastructure. The attacks caused serious damage, particularly to surface infrastructure, tunnel entrances, production facilities, and launch systems. But eliminating the underground system entirely was a different problem. One of the most striking examples of Iran's underground warfare concept emerged in Yazd, in the central part of the country. The Imam Hussein Strategic Missile Command Center, built into the mountains south of Yazd, had become one of the key centers of Iran's long-range ballistic missile force. During the war, U.S. and Israeli air forces repeatedly bombed the mountainous area around Yazd for approximately 40 days. Yet the attacks failed to halt missile activity completely. Open-source data and reports from the region indicated that missile launches continued from the area even while the bombardment was underway. Satellite images taken after the war showed that damaged tunnel entrances had been cleared, roads reopened, and work to return the facilities to operation had begun rapidly. This is where the importance of the Yazd example lies. Iran did not simply store firepower underground, it moved an entire war support infrastructure inside the mountain. Thus, even if the attacker destroyed entrances, roads, and facilities outside the mountain, eliminating the entire system inside became much more difficult. The success of underground facilities should therefore be measured not by whether they are hit, but by whether they can continue fighting after being hit. The inability to silence missile activity completely, despite roughly 40 days of bombardment around Yazd, is perhaps one of the strongest examples of how mountains and underground spaces have once again become strategic defensive domains in 21st century warfare. According to American intelligence assessments reported after the war, Iran was estimated to have preserved approximately 70% of its pre-war mobile launchers and missile stockpile. It was also reported that some tunnel entrances were reopened after being struck and that missile launches resumed from the same areas.
The fundamental objective of Iran's underground strategy was to prevent its missile force from being completely destroyed. Viewed from this perspective, the system largely fulfilled its function. The central lesson of the Iranian case is that modern underground defense is not simply a matter of digging deeper. The approach seen at Fordo and Natanz, for example, is based on using the mountain mass itself as natural armor, placing facilities beneath tens of meters of rock, constructing long and changing access tunnels, separating critical sections from one another, and creating multiple entrances and ventilation systems. Protection thus becomes a multi-layered architecture combining depth, compartmentalization, redundancy, and natural geology. Concrete is important, but it is not the sole determining factor in such a system. The exact grade of concrete used in Iranian facilities has not been verified through open sources. Nevertheless, it can be said that in modern protective structures, high-strength concrete in the range of 60 to 120 megapascals, and in more advanced applications, UHPC or UHPFRC classes exceeding 150 megapascals, can provide significant protection.
The key lesson from Iran is therefore not simply to build an extremely strong concrete wall, but to combine high-strength concrete with tens of meters of natural rock, depth, compartmentalized galleries, and a redundant tunnel network. Air superiority is not everything. The Iran-US-Israel war revives an old military question. Does air superiority mean dominating the entire battlefield? Because of the devastating firepower and shock it can generate on the surface, air superiority usually provides a major advantage. But when the battlefield expands underground, the equation changes. An air force can strike an enemy's runways, radars, energy facilities, air defense systems, and surface missile launchers. Yet if a major share of the enemy's combat power lies beneath tens or hundreds of meters of rock, the targeting effort becomes different. First, the entrances must be found, then the geometry of the structure must be understood, and finally, the appropriate munition must be used. Moreover, collapsing an entrance does not necessarily mean that the facility itself has been destroyed. In Iran, some facilities appear to have been damaged to the point of temporary suppression rather than complete destruction. Given sufficient time and repair capability, Iran was able to reopen some entrances. There is a major strategic difference between silencing a missile base for a few days and eliminating it in such a way that it cannot be used for the remainder of the war. That difference arises from the difficulty of destroying well-protected caves and underground shelters with conventional weapons. Similar examples of the Iranian experience can be seen today in China, North Korea, Russia, Ukraine, and elsewhere. As satellites, UAVs, persistent surveillance, artificial intelligence, and precision strike systems make surface activities increasingly observable and lethal, the strategic value of operating underground rises.
Therefore, alongside long-range missiles and advanced dome-type air defense systems described with various labels such as iron, steel, or golden, the military infrastructure of the future will include underground and protected command centers, ammunition depots, armed UAV hangars, missile launchers, production facilities, and logistical infrastructure. In other words, the battlefield is becoming vertical as well as horizontal. Underwater, the same basic dynamic that drives forces underground on land is operating at sea. What is visible is becoming easier to target. Satellite reconnaissance, UAVs, radars, electro-optical systems, and AI-assisted targeting are making the surface increasingly transparent. As long as a warship remains on the surface, it stays inside this detection and targeting network. A submarine's greatest advantage, before firepower, is invisibility. In this sense, depth at sea provides what mountains, caves, and underground shelters provide on land. Both reduce visibility, limit the effectiveness of sensors, and complicate the adversary's targeting chain. The history of naval warfare is full of examples. The reason the Gallipoli campaign, which contributed to extending the First World War by 2 years, began was that on March 18, 1915, the joint British-French invasion armada failed to pass through the Dardanelles because of the 26 mines laid by the Nusret. Mines waiting beneath the surface changed the course of the war. During the Second World War, American submarines played a critical role in the collapse of Japan's economic and military logistics by destroying a large share of the Japanese merchant fleet and maritime transport system in the Pacific. In the Atlantic, German U-boats attempted to sever Britain's lifelines. This is why Churchill said that the only thing that truly frightened him during the war was the U-boat threat. The strategic power of the submarine came from its ability to threaten a military and economic system far larger than itself without being seen. 80 years later, this physical advantage has not disappeared. Despite extraordinary advances in artificial intelligence, big data, satellite systems, and unmanned vehicles, the complex rules of acoustics still prevail underwater. Water temperature, salinity, pressure, layer structure, seabed topography, and ambient noise all complicate the detection problem. For this reason, the submarine's most important weapon is not its torpedo or missile, but first and foremost its ability to remain undetected. This is also the fundamental reason why ballistic missile submarines remain the most survivable leg of nuclear deterrence. In the second quarter of the 21st century, underwater competition is no longer limited to manned submarines. Unmanned underwater vehicles, UUVs, long-range autonomous underwater vehicles, seabed sensors, and underwater communication systems are creating a new ecosystem. Just as possessing submarines in the last century was a strategic capability available to only a limited number of states, in the coming period, the ability to operate long-range, independently functioning autonomous underwater systems together with manned submarines will create a similar divide. The next stage of underwater competition is seabed warfare. Intercontinental fiber optic cables, energy pipelines, electricity connections, sensors, and communication systems are located on the seabed. Thus, in the future, the underwater domain will not merely be an environment in which submarines hunt surface ships and other submarines. It will become a separate strategic front containing critical infrastructure, unmanned systems, and operations conducted against them. As the battlefield expands upward into space, it is also expanding downward toward the ocean floor.
After surface operations become increasingly transparent, the great technological race will shift toward who can see underwater first. For this reason, it is not sufficient to understand future naval warfare merely in terms of more ships or more unmanned surface vehicles. The main struggle will be shaped by which side can remain unseen, detect the opponent first, and keep its own command and control system alive under attack. The survivability concept demonstrated by Iran's missile cities on land and the invisibility provided by submarines at sea are in fact two different applications of the same strategic principle. As the surface becomes more transparent, warfare shifts into depth. In the future, superiority will belong to the side that can hide in depth, see into depth, and control depth. Therefore, when the defense architecture of the future is debated, the question of how combat systems can survive must be discussed just as seriously as the systems themselves. Iran's 2026 war should be studied carefully from this perspective. Conclusion. The unchanging dialectic of military history is the competition between firepower and survivability. As artillery improved, trenches grew deeper. As air power developed, fortifications moved underground. As reconnaissance and surveillance capabilities expanded, camouflage and deception methods evolved. Today, the combination of satellites, radar, UAVs, electronic intelligence, artificial intelligence, and precision-guided weapons is making the surface more transparent than at any point in history. The natural consequence is flight from the surface. From the shallow tunnels of Ku Chi during the Vietnam War to North Korea's mountains, and from Gaza's underground network today to Iran's missile cities carved into rock, the same historical trend can be seen in different stages. The Iran War revealed the strategic dimension of this transformation.
Underground facilities do not provide absolute immunity, but they greatly increase the time, ammunition, and intelligence effort an attacker requires to locate, strike, confirm damage to, and strike them again. Underground space is therefore no longer merely a shelter. It is a distinct domain of warfare that erodes technological superiority and enables strategic firepower to survive. After these experiences, military geography assessments will inevitably place greater emphasis on mountains with caves and other natural areas capable of providing concealment and protection. This is also an important model of defense architecture for Turkey to consider. Turkey's geography offers significant natural advantages in this respect. The Taurus Mountains in particular, with their broad and thick mountain masses, form a natural cover that can be compared in some respects with Iran's Zagros Belt, while the high and rugged mountainous regions of eastern Anatolia offer similar potential. Cappadocia, as demonstrated by Darren Kuyu and Kai Mockley, historically proves that it is possible to create very large underground volumes in Anatolia. However, because of the mechanical properties of volcanic formations, the Cappadocia model should not be regarded as being in the same category as the protection provided by hard rock masses. The main lesson Turkey can draw in this contest is not simply to convert existing caves into shelters, but to make mountains and geology part of defense architecture. The Taurus Belt in particular offers noteworthy natural potential for such an approach. At the same time, the suitability of an underground facility cannot be measured solely by the height of the mountain above it. Rock structure, fault and fracture systems, earthquake risk, groundwater, and long-term structural stability must all be evaluated together. The same transformation is now taking place beneath the seas.
With submarines, unmanned underwater vehicles, UUVs, fixed and mobile sonar networks, seabed sensors, cables, pipelines, and energy connections, the underwater domain is increasingly becoming a battle space in its own right. The struggle of the future will therefore not be only a flight into depth, but a struggle for control of depth.
While one side attempts to hide from sensors by going underground or underwater, the other will try to make these domains transparent again through seismic and acoustic sensors, sonar networks, unmanned systems, satellite data, and artificial intelligence. One of the central military questions of the 21st century will therefore be, after making the surface transparent, who will make the depths transparent? For many states, the objective will be not only to build underground infrastructure capable of surviving the first strike, but also to create an integrated underwater domain awareness architecture that can see, map, protect, and when necessary, use the underwater environment. In summary, Turkey should use underground and underwater domains as force multipliers in the great power struggles of the 21st century.